So, Ajwat, ready ya?
Doktor, kejap. Saya
Dah boleh
kena
start share dah.
sekejap. Saya kalau tak ada background tak apa. Doktor. Sebab saya
Kalau
guna daripada browser. Webex ni daripada browser, so tak ada option untuk buat background tu. Letak
tak apa,
background.
no problem.
Okay.
No problem.
Ya, saya try share slide saya.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Very good afternoon, especially for those who come from Malaysia or in the neighboring region in the same time zone. So we are now in the afternoon. So I think every single of us will definitely have a good lunch. So welcome to session number 4. So here you have me as a chairman of the session 4. Let me introduce myself. My name is IR Dr. Muhammad Nazri bin Muhammad Nasir. So I'm one of the COE or Center of Excellence Aerolab members, and also head of UAV, Unmanned Aerial Vehicle Laboratory. Is a subsidiary of UTM Aerolab. So we are very happy today that we have all together, I think 1, 2, 3, 4, 5, 6, 7, 8 presenters. So before we make a start, so let me brief you a few things. So the first thing I would like that, if possible, please introduce yourself. Okay, maybe you can write down your paper ID in the chat box. Together with the paper ID, your name and also your email address. So let's say any of the audience, if they have a further question, they can just simply email you and then contact you, after we complete the conference. So that's one thing that I would like ask you a favor. And then about the times, I think every single of us will allocate 20 minutes, okay? So 20 minutes will be allocated for every single presenters. So that's include Q&A. So I suggest that please give 15 minutes of presentation and another 5 minutes for Q&A. So that will definitely help the organizer to ensure that our event will always be in schedule. Okay, so and then another thing is I also request a favor from the participant to suggest the best presenter. Okay, so you can put the vote in the chatting box. Either you want to declare to everyone, or you can declare or you send the rank the best. Only give the best. Okay, just give the best paper ID personally to me. Okay, just write the paper ID and then send it personally to me through chat box personally, or also to the other people if you want to declare to the other people. Okay. So I think without any further delays, so please Muhammad Ajwat. Okay, so Muhammad Ajwat can start. Open your presentation slide. Please share your presentation slide. Okay, so Muhammad Ajwat here, the paper ID will be paper number 12. Okay, paper number 12. And the title of the presentation that Muhammad Ajwat will present later, entitled Simulation of Study on the Performance of all tech using a different working fluid or the different refrigerant. So Muhammad Ajwat is one of my student under my supervision. So together with him, we have me as a supervisor, and then Dr. Norazila and also Dr. Shabuddin. Okay, so Muhammad Ajwat, you still with us? So please share
Yes.
your slide.
Okay, share first.
And once everything's okay, then you can immediately start.
Can you see my slide?
Make in the presentation mode, and you can continue. The floor is now, Muhammad Ajwan. You can start.
Okay, is the slide is in the presentation mode?
Not yet. It
Oh,
might take some time, I guess. Otherwise, you can just start. Maybe there is a problem somewhere. No problems. I think it's big enough, and you can continue.
okay. Just want to confirm if I scroll down, the slides change.
Not yet. No.
Okay. The slide froze.
Okay. Let's move to the second slide.
Okay.
This is an introduction background study.
Okay, may I
Go
start
back to
now?
the front page. Okay, you can start now, Muhammad Ajwan.
Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and very good evening to all. My name is Muhammad Ajab Mahinuddin. I'm a master student in University Technology Malaysia. So today I'm going to present my technical paper with the title of Simulation Study on the Performance of OTEC using Different Working Fluids. I will start with the introduction. So, as we are all aware of, renewable energy has become a prospect medium to replace fossil fuels for electricity generation. So, this is because the continuous usage of fossil fuels give a negative impact to our environment, such as the global warming. So there are several types of the renewable energy that we have known of, but the one that I'm going to focus on is what we call the ocean thermal energy. So basically, this ocean thermal energy existed due to its exposure to solar energy, which causes a temperature difference between the surface part of the ocean and the deep region part of the ocean. So this temperature difference can be exploited uh, to produce electricity through a system, what we call the Ocean Thermal Energy Conversion System, or OTEC system for short. So the basic idea of this system is that we use the seawater at the surface part of the ocean and to be used as a heat source to heat up the working medium in the cycle, so that the working medium will change its phase from liquid to vapor phase, and the vapor will expand in the turbine and produce electricity, and then it will flow into the condenser to reject heat to the medium with much lower temperature, which in this case is the seawater that we obtain from the deep region. And then the working medium will change its phase back to liquid form and will be pumped back into the evaporator to continue the cycle. So despite of having great benefits of using this system, there is one major issue, which is it is very low in thermodynamic efficiency. So according to previous studies on OTEC, the uh, there's only a range of about 2 to 5% in thermodynamic efficiency, which is very low. So how to overcome this issue? In this study, there are two things that are going to be considered. The first one will be the selection of the working fluid. So working fluid is a very important medium in an OTEC system because different working fluid has a different thermodynamic or thermophysical properties, which will give a different degree of performance. So another thing that we will be look at will be the parametric analysis. As we all know, parametric analysis is a method to identify how much the parameter value changes that influence the changes in the parameter in the performance. So in this case, one of the critical parameters that we will be going to study is the turbine inlet parameters, specifically on the temperature and the pressure at the turbine inlet. So there are many studies that says that this parameters at the turbine inlet give a significant effect on the cycle performance. So the objective of this study is first is to determine the optimal working fluids that fulfill the criteria of low boiling point, high critical temperature, and low in ozone depletion potential and global warming potential. This will be explained detailed in the methodology. The second one is to analyze the performance of a low power range OTEC system by using the selected working fluids through a parametric study, which is the turbine inlet parameters. And lastly is to evaluate the performance of the OTEC system in terms of the thermal efficiency and net power output. So for the methodology, it starts with the selection of the working fluid. Firstly, the working fluid is categorized into 3 different groups, which are the dry, wet, and isotropic, and then further filtered by following the requirement of the boiling point of less than 30 degrees and the critical temperature higher than 60 degrees. So this value is taken from the previous studies, just an indicator, because we wanted the working fluid to be able to boil using the temperature of the ocean. And also we want to prevent from the working fluid from having a irreversible exchange, because if the working fluid is heated above the critical temperature, then the working fluid cannot change its phase back to the original form. So we also consider the ODP and GW value to be low, because we wanted the system to have a very low environmental effect. And we can see here at the right side, we have the table of the selected working fluid, and also the graph for the thermophysical properties for each working fluid. So this is the graph of the specific heat capacity, the thermal conductivity, and latent heat. And after we have decided all the working fluid, we'll proceed with the parametric analysis, where, as I mentioned earlier, we focus on the turbine inlet parameters, which is the turbine inlet temperature and the turbine inlet pressure. And we will compare all the results given by each working fluids in terms of the thermal efficiency and net power output. This is the assumptions and the operating condition for the OTEC. And this is the schematic diagram of the basic OTEC cycle that has been modeled in the simulation software, which is DWSim. And also, this is the TS diagram for the basic OTEC cycle. So for the research fundings, the first one would be the turbine inlet temperature versus the thermodynamic efficiency and net power output. So as we can observe from the both of the graph, it can be said that the working fluid R717 or ammonia give the best results in both thermodynamic efficiency and net power output, with the 6.6% in efficiency and 9 kilowatt in power output. So these results can be related with the working fluids thermophysical properties, because according to Mago, it stated that the thermophysical properties, such as mentioned earlier, the specific heat capacity, the latent heat, and the thermal conductivity has a direct relationship with the cycle performance. So if the value of these thermophysical properties is high, meaning that the performance will also gives the best results. So since the ammonia has a much higher value in these thermophysical properties compared to other working fluids, so it gives the highest results in the efficiency and power generated. And for the turbine inlet pressure versus the thermodynamic efficiency and net power output, we can see here that ammonia once again gives the best results with the efficiency of 5.3% and the power output of 7 kilowatt. And the other things that we can observe from the graph is that ammonia has a much wider operating pressure compared to other working fluids. For example, if you compare with the R1234ZE in yellow color, it has a much steeper slope. This indicates that the ammonia is flexible to be used without having a problem, without having to concern about a sudden drop in performance. So also we can see in the graph that each working fluid has their own maximum value and have a decreasing pattern as the pressure increases. So this means that the operating pressure of the system has exceeded the working fluid saturation pressure. If the operating pressure is higher than the saturation pressure, then the working fluid will have a state of liquid at the inlet turbine. Sorry. So we know that we cannot have a liquid droplets in a turbine because it will damage the turbine blades or corrode the turbine blades, and at the same time will reduce the performance. So in conclusion, we can conclude that the ammonia has the best results in thermodynamic efficiency and net power output when we are manipulating the turbine inlet parameters. However, the only consideration when we are using ammonia in the system is that the first one, ammonia is very toxic. So it may be hard in terms of handling. And the second one is that when we see at the previous graph at the turbine inlet pressure, we see that the ammonia needs to be operated in very high pressure, meaning that we need to have a very high performance equipment, which will not in favor in terms of cost. So that are a few downside when we are using the ammonia. And lastly, as we can observe from the previous slide, each working fluid has a maximum value. So an optimization approach can be done in the further studies when in a certain requirement of the parameters. So before I end, I would like to thank you to the SATRAP's OTTEC program, which is led by UTM Ocean Thermal Energy Center, for funding me and for enabling me to present in this conference. So SATRAP's is basically a program, a collaboration program between the Japanese government and the research institute in order to solve problems in terms of environment or any other things that related. So with that, I thank you.
Okay, thank you very much, Mr. Muhammad Ajwad bin Wahinuddin. So if we continue, so for the next part, do we have any question from the fellow audience? Please, one or two questions for Muhammad Ajwad. You don't have to be very specific or very technical. Introductory question also welcome to motivate Muhammad Ajwad and his team. Prof. Afifi, maybe? Since you already opened the camera.
To ask, this ocean thermal energy conversion, at what depth of the ocean can you achieve such? Because you want to heat the ammonia, or want to vaporize it to a gas turbine working fluid. At what depth of the ocean can you achieve this?
So basically, the standard depth for the ocean is about 1,000 meters, which is about 1 kilometers, and the temperature of the seawater at that depth is around 5 to 8 degrees. So yeah.
When you mention 1,000 meter, that Indonesian submarine tracked at what 400 meters. So what must be the structure like to stand all this to be at 1,000 meter or 1 kilometer under the sea? Remember last year, an Indonesian submarine get lost when it was sinking to about 300 meters, something like that. So the structure, the cost, I don't know how much the cost for such a conversion unit.
Yes. Actually, the cost is for the structure just to get to the depth, that certain depth is very costly. It's very expensive, and but I'm sorry to get I cannot give that answer because I did not specify on the costing.
Yeah, it's all right, but then you have to sell your electricity at a much higher price to the customer. I don't. Okay. It's all right. It's all right.
Okay, thank you, Professor Afifi. So, any other question from the audience? Okay, so if not, then we move to the next presenter. So before that, I would like to say thank you again to Mr. Muhammad Ajwad. Okay, so now we move to paper ID number 14. So the title of the presentation, Structural Analysis of Radial Turbine Impeller for OTEX. So here we have the names of the authors and his co-workers. So Isaac Hussaini, and then we have Abdul Latif. So this is Professor Ainul Lofi. And then here we also have Mr. or Dr. Muhammad Fairuz Samsudin. So this is also from the same research group, SATREP. So without any further ado, so let move to the next presenter. So Mr. Iskandar, okay, so we used to call him Mr. Iskandar Jr. to differentiate between him and Dr. Iskandar Ishaq. Okay, so you can start, share your slide and maybe give greetings to the fellow audience. Try to switch to presentation mode if possible. At the same time, say hello just to test the audio. Is it working good or not?
Hello, can you hear my voice?
Okay, a little bit louder.
Assalamualaikum.
Waalaikumsalam. We hear your voice.
Okay.
If possible, make it a little bit louder.
Can you switch on to presentation mode?
This is presentation mode.
Uh,
Is this mode?
you change kat atas tu dekat
Slideshow lah.
slideshow. Dekat dia you have got to dia pergi different screen ni.
Or maybe you can go to you press the play button mode here at the below. Yeah, that one. That's not changed to the slide presentation mode.
No, I think dia punya screen tu. Switch the screen.
But I think he's using laptop and definitely have one screen, unless he has a second. Okay, that's working good. Okay, so without any further delays, so Mr. Iskandar, you can start 20 minutes from now.
Okay, Assalamualaikum everyone, and a very good afternoon to Prof. Ainul and my fellow colleagues here. Thank you for joining my presentation. Today I will be presenting about the structural analysis of radial turbine for thermal energy conversion system. So my name is Iskandar Zulkarnain bin Muhammad Saini. So I will present about OTEC, the radial turbine for OTEC. So firstly, are you all familiar with the OTEC system? I think Ajwad presented earlier about the OTEC. It's actually a renewable energy source in the ocean surface, and the OTEC system uses organic rankine cycle. So in this organic rankine cycle, there exists 4 components, and the turbine is one of these components. So the turbine actually is experience many types of loads. such as pressure, centrifugal force, and also vibration. So my concern is about the structural area in this turbine. Mainly focused on the impeller part of the turbine. So my method to determine the effect of the loads is using finite element methods, which use static analysis, model analysis, and also frequency response function. Okay, so this is the general overview of the OTEC. And as you can see on the right there, the above, the second image, there is our turbine unit, and the below it is the impeller that I mentioned. So in the, you can see the impeller, ammonia, working fluid of ammonia will pass through the volute, then will hit the impeller blade, and the impeller will also spin at a high rotational speed. So these are the loads that I am concerned to make sure that the turbine works in safety and also doesn't avoid failure at during working condition. So our aim is to make a turbine rig that can withstand the normal working condition given to us. So a turbine usually has a volute, a stator, and a rotor. So the rotor is also another name for the impeller, and I will use this model on this impeller model. So my objective is to discuss the effect of different loads on the impeller during two critical conditions. So firstly, when the first condition is the startup condition, where the pressure on the blade is at maximum. So this is also called as stagnation pressure. And the second condition is during the during the running condition, when the machine is actually running and the rotational of the impeller is at maximum speed. But also there exists pressure. The pressure also exists, but it's lower than the previous condition. So the scope of my study is only to improve the parameter consideration of the turbine, because the turbine model that I use actually is already topologically designed, considering the highest performance and net power output by a colleague of mine. So in the study, the parameter that I will vary on the impeller is the blades, the thickness of the blade, and the type of material used. So in this study, I will use stress analysis, model analysis, and frequency response by using finite element method. So this is my map of my method to do the analysis. And I will share the loading conditions of the turbine impeller. Firstly, during startup condition, you can see there the red area, the working fluid will hit the suction area of the impeller, or about 800 kilopascal of pressure. So, and after that, when the blade will slowly start to spin and finally achieve a uniform speed of 500,000 rotation RPM, but also has a lower pressure of 630 kilopascal. This is the boundary condition of the model. So the first model that I use is the blade of the impeller. So this blade will be the element used is a shell element. Why do I use shell element? Because the shell element is easier to change the thickness, and I use 4 different values of thickness, which is 0.5 mm, 1 mm, 1.5 mm, and 2 mm thickness. So other than that, the material that is considered for this impeller is aluminium, titanium, and stainless steel. So the boundary conditions, as you can see from the figure above, the blades will be fixed to the hub of the impeller, and the impeller also will be fixed to the shaft. So as always, to minimize the error during analysis, we must do a mesh convergence study. So I have found out that the mesh size of both models to be 0.15 millimeter and 8,555 number of elements. And for the second model, we use a mesh size of 1.4 millimeter and 64,265 number of elements. So in the first study, in the first analysis, that is the stress analysis, I found out that the safety, the blade thickness, as you can see on the left, the blade thickness is safe to use is 1 millimeter for every material, and the best margin of safety falls to the blade thickness of 1 mm made by stainless steel, and the maximum stress acting on it is 84.35 megapascal. So this is below the yield strength of stainless steel by a significant amount. So actually, it is very safe to use this material and this thickness. Next, we can see the critical area where when the load is applied to the blades and the impeller. So as you can see, at the root part of the blade, that is the critical part, but the stress experienced by it is very much lower than the yield strength. And for the turbine impeller, the part is actually at the hub also has a very low stress magnitude. Next, I will present the mode 1 frequency, which is the lowest natural frequency. So in the mode, in the frequency of the impeller for the aluminium is 6,063, aluminum around 9,700, and stainless steel 9,200. So when the impeller rotates for 50,000 RPM, the frequency range of operating range of frequency is 8,300. So as you can see, aluminium already fail or can fail during this operating range, and titanium and stainless steel is safe for 50,000 RPM. So this actually improves our precision on the using of stainless steel. The magnitude during the mode 1, the displacement magnitude is also very little, which is 5 5.05 micrometer. So in this range, the 5.05 micrometer is also very small, and it's inside the tolerance of the turbine unit, so that the turbine blades does not hit turbine casing. So as you can see on the left, during the first mode around the 9,200 hertz, the displacement is very little, but it ramps up at the frequency mode of mode 3, which is actually still very small, around 14 micrometer. So I conclude that the impeller that is designed is safe to use in this operating range, and I conclude that stainless steel is the best. Stainless steel is the best material made of 1 mm thickness. It's safe within operating limit. So the stress that is experienced is very less than the use strength, and it has a very good margin of safety. And the critical area is at the tip of the blade, and this displacement at this tip is also is within the allowable tolerance. That is all I wish to share today. Thank you for listening.
Alhamdulillah, thank you very much, Mr. Iskandar. So now we still have a few minutes for the audience to ask a question to Mr. Iskandar Zulkarnain. That's the name that I'm looking for. Because you put in the short form, then it will be difficult for me to recognize you. I just know that Iskandar. Okay, Iskandar Zulkarnain, please ask question for Mr. Iskandar.
Can I ask, what is the diameter? What is the inlet eye diameter and the outlet diameter of your turbine?
Oh yeah. So the inlet we have in the design condition, our friend here Rajan, he designed the inlet to be 40 mm, 45 mm.
40?
45.
The eye diameter is 45 millimeter. And the outlet?
Outlet,
But
I need to recheck.
yeah, okay. Okay, physically, have you seen such a radial blade? Since you're working research on it, have you handled in your hand such a radial blade?
Yes, sorry?
Have you seen such a radial blade with 45 millimeter inlet and about, I say, 60 millimeter outlet? I think maybe 60 or 70.
Have I researched?
Have you seen it physically? Since you're working research on it, you must be able to have a look.
Oh yeah. I already printed and all. I already made our team already made it.
You mentioned the turbine blade. Oh
Yeah.
What I may suggest is this: you go and buy an automotive turbocharger. Just take the turbine part.
Yeah. Actually, there's also a consideration in our. We are just taking the unit, the turbocharger unit, and we change the impeller because
Many this cabin, what your crew cab, Toyota, Hilux, all this, and all those are turbocharged engine, and they make very good turbocharger. So take the turbine there.
Yes, actually that's also the consideration because they made the turbocharger very, they have tested it, the vibration, so we the bearing unit is suitable for us. So we just need to change the my part lah. the critical condition.
I saw
balance.
you say your RPM is 50,000. 50,000.
Yeah.
RPM.
Yeah,
You
that is
need
the
expression.
challenge of our team.
Very okay.
50,000 RPM.
Thank you.
Okay, maybe from other audience. Okay. Okay, thank you very much, Mr. Iskandar Zulkarnain. Okay, so master student from a SATRAP program under supervision of Prof. Ainul and also Dr. Fairuz. Okay, so very soon Mr. Iskandar will defend his master thesis. So please pray for him, and I wish him good luck. Okay, so now we move to the next presentation. So here we have the paper ID number 20. So the title of the presentation, or the topic of the presentation, is Impact of Solidity on Aerodynamic Performance of Vertical Axis Wind Turbine. And the authors is Ko Hui Wong, Shen Kai Ung, Yong Hua Tang, Jo Han Eng, and Wang Tong Chong. So I'm very sure this is from group Prof. Chong Wen Tong. Okay, so Prof. Chong Wen Tong used to be our student before. So now Prof. Chong in University Malaya. So he's one of the Malaysian expertise in wind turbine design and also fabrication. So please start sharing your slide.
Okay, thank you, Dr. Nazri.
Okay, you can switch to presentation mode and immediately start the presentation, and you have 20 minutes for the presentation together with Q&A. So
I see. Okay, now.
Good. The voice is very good, and I think yes, you can start now. Everything perfect.
Okay, thank you. So, Assalamualaikum and good afternoon to everyone. My name is Tang Yonghua, and I'm a first year undergraduate student from University of Southampton, Malaysia. And my topic is the impact of solidity on aerodynamic performance of vertical axis wind turbine. So a little bit of background on vertical axis wind turbine, or we call it as VOT in short. So there are two types of VOTs, which is lift type Darius or drag type, which is Savonius. As you can see, a few examples here. For Darius, we have egg beater or hash rotor. And for Savonius, we have something like a concave blade. And we also have a hybrid, which is a combination of lift and drag type VOTs. And there are some advantages and disadvantages of VOTs. So the pros are VOT is omnidirectional, and it does not require yaw mechanism as compared to horizontal axis wind turbine, where it needs to yaw to face the wind. And it generates power more efficiently at low wind speed, more suitable to turbulent wind conditions such as urban onshore area. It generates low level of noise, easy to maintain, repair, and retrofit, and it has low sense of gravity, so it's a good safety issue. But it has some disadvantages such as lower efficiency, especially for Savonius rotor, because the wind will impinge on both sides of the blades. And also for Darius rotor, the inability to self-start. And for the research methodology, these are some of the equations for aerodynamics. As you can see, for example, T-speed ratio, lambda, which is R omega, the tangential velocity of the tip, over U infinity, which is the free stream velocity. And we have coefficient of torque, coefficient of power, which is lambda times Ct. We have power and solidity, sigma equals NC over 2R. And this is the core of our research. and we try to manipulate the n number of blades and c the chord length. So we try to simulate, to model. We simulate the wind tunnel test data published by Castelli in 2011 using ANSYS Fluent CFD software. And we are using a 3-bladed hatch rotor bolt with NACA 0021 aerofoil. As you can see, this is how it will look like in real life. But actually, we are using 2D simulation. And these are some of the parameters. And we plug in the equation for solidity just now. We can get 0.25. And for the domain size and boundary condition, we have 2 domains, which is rotor and stator. The rotor, the circular one, as you can see in this middle, it comprises the volts, and the rotor mesh size is 1.5D, and the stator, the outer large rectangular one, is 20D times 30D. And the side wall we set as symmetry. The volt blade is non-slip, and there's a boundary between rotor and stator we set as interface, so we can perform the sliding mesh method. And the rotor domain is placed 10D from the inlet and 20D from the outlet to allow full development of the wake. And the blockage ratio is 5% for bare turbine, which is less than the upper boundary of 6 to 7.5% for numerical simulation and 10% for experiment. And this is from Lam and Peng in 2016. And these are some of the computational conditions. As you can see, we use pressure-based, time transient. Simulation space, we use 2D. Turbulence model, we use K omega SST, which is K omega in the near blade region. And for the far field, in the free stream, it switches to K epsilon. Blade motion type is moving mesh, inlet velocity 9 meters per second. And for the pressure velocity coupling, we use semi-implicit method for pressure link equation, which is simple algorithm. And for the interpolating scheme, we use second order upwind. And transient, we also use second order, so it's more accurate. And the residual error, the log of residual error is -5. So fine mesh is desired for accurate results, but it may cost long computational time and have large storage space. And the volt rotor mesh consists more than 80% of quadrilateral cells combined with high aspect ratio cells near the inflation layer. So the first layer thickness near the blade was set as 0.05 millimeters to obtain a Y plus value of less than 5 and approaching unity, which is 1. As you can see, this mesh independency test. So we have 6 mesh, and we simulate at different TSR to obtain the coefficient of torque results. As you can see, C5 and C6 from this graph, they have almost the same results. So we prefer C5 to save some computational efforts. And for the validation, a good agreement between the simulation and the wind tunnel experiment by Castelli. As you can see from this graph, there's a slight discrepancy, and it's most likely due to the tip losses of the rotor blade and the rotor spoke effects that were not captured by the CFD simulation. And in addition, the geometric simplification of the rotor shaft has contributed to this over-prediction, and such similar observation has been reported in literature. So we are now looking at the effects of solidity at the coefficient of torque per blade, and we are now changing the number of blade. As you can see, is analogous to express as partial derivative with respect to n, while we keep the chord length constant, which is 85.8 millimeters. Okay, so as you can see, the number of blade increases, the CT max of each individual blade decreases due to significant blade-to-blade interactions. And for the single-bladed boards, the blade-to-blade effect virtually does not exist. And this is the sum coefficient of torque, which is similar as the previous, but we are summing all the blades together, depending how many blades it has. So when the number of blades is increased, the CTmax value increases with an optimal configuration of 3 blades, which is CTmax is 0.13, as you can see from the figure, the green one. However, when the number of blades is further increased to 5, the CTmax tends to decrease. And the occurrence of CTmax is gradually shifting towards a lower TSR, which is left-hand side, with increasing blade number. And this phenomena is due to a lift-to-drag ratio of low solidity boards being higher than the high solidity boards. And a higher number of blades produces more drag and less lift, which lowers the torque and power output of a watt. So furthermore, watts with higher solidity shows a smaller operation range in terms of TSR. Now we look at the sum coefficient of power. So as the solidity increases from single to two-bladed watts, the CP max value increases, but further increment of blade number will deteriorate the performance of the watts, and the occurrence of CP max is also shifted to lower TSR. And the greater CP max occurs at two-bladed watt, which is approximately 0.41. So this indicates that low solidity watts are more suitable to operate at high TSR, whereas for high solidity watts, they perform better at low to moderate TSR. And decreasing the blade number can reduce the blockage effect and the blade weight interaction, but the self-start feature suffers. So you can see the three-bladed has the maximum CT, and the two-bladed has maximum CP value. Now we look at the effects of solidity at the sum coefficient of torque by changing the blade torque length, and we keep the number of blade constant, which is 3. So 3 different chord lengths of C, 2C, and 3C were investigated, which correspond to the solidity of 0.25, 0.5, and 0.75. And similarly, CTmax is shifted to a lower TSR as solidity increases. So this denotes that a vault with longer chord length has better self-starting ability than a vault with short chord length. And also the gradient is steeper for longer chord length vaults, which is high solidity turbine, but it will only covers a narrower TSR range compared to a low solidity vault. So it can be concluded that regardless of the number of blades, when the solidity increases, a similar trend is observed. So if I want to use 3-bladed, if I use 1-bladed or 5-bladed, then we will also observe the similar trend. So we now look at the effects on sum coefficient of power. So the CP max is almost having the same magnitude regardless of chord length. And the CP max for a high solidity vault happens at a lower TSR. And at low TSR, the lift is the dominant factor affecting the blades at low rotational speed. However, when TSR increases, the rotational speed of the blade increases, the drag force becomes more dominant. And the longer the chord length, the more dominant the drag is acting upon the blade surface. So such vault displays lower performance, which is it will operate at lower TSR range. So you can see the chord length 3C has the maximum CT, and the 2C has the maximum CP. And we now look at the vorticity contour plot by changing number of blades. So vorticity is just simply the curve of the velocity vector field. So for a single blade, volt configuration, the rotor blade travels with the minimal interaction with the vortices. And as the blade number increases, it's noticed that the vortex shedding on the blade becomes significant and closer to the subsequent blades. The angle of attack on the blades is smaller at higher TSR due to larger relative velocity, and the dynamic stall is less significant. But when the blades are rotating faster, the rotor interacts with the wake more frequently, so it reduces the performance of the rotor, especially when the solidity increases. At moderate TSR, a turbine with a high number of blades could generate higher power output as the rate of interception of blade with the wind is more. Now we look at the effects on changing the chord length. So as the blade chord length increases, the vortex shedding on the blade becomes more significant. At high TSR, the blades interact with the vortices more frequently, which causes the CTmax to happen at a lower TSR. So in summary, there's a good agreement between the simulation and experiment. And when the solidity increases, the maximum CT and CP increases up to an optimum point. But if the solidity is further increased, it will deteriorate the performance of the rotor. And a high solidity volt assesses CPmax at a lower TSR. So a high solidity volt is suitable for low TSR environment, while a low solidity volt performs better at high TSR. And high solidity volt could produce larger torque output with better self-start ability. And lastly, as solidity increases, the TSR operation window becomes narrower and vice versa. So that's all from me. Thank you.
Thank you very much, Mr. Presenter. So now I open for Q&A from audience. So please ask question. Any question? Maybe Dr. Nick?
See, it was interesting because I was working on this in 1976. You know, the vertical axis wind turbine, the radius rotor, whatever it is. So there was a suggestion. There was, because I left the university, they were thinking of putting a cam mechanism at the center of the rotor, so that as the blade rotates, the angle of incident of the blade, they are using an ACA 0012, so that the incident of the blade changes. Because if you put a fixed blade, the one that is facing the wind directly will get all the lift force and this thing, the one that contributes to the rotation. Then what changes position, it becomes a hindrance and become a drag. So why not put a cam mechanism in such a way that the blade angle is changing with the position of the blade around as they rotate? That may help. I don't know, it's a suggestion. And I look at it, you know, if you go to Penang, the Penang ferry got a similar type of propeller. They call it VSP, Watch-Schneider propeller. It's a vertical axis propeller. And they change the angle of the pitch. They have 6 blades or 5 blades. They change, that's why the ferry can move sideways, forward, reverse, everything. And remain stationary with the propeller rotating. So that was the idea, putting that into the blade of the vertical axis, putting that cam mechanism that will control the blade angle. Then take more torque, contribute more torque, maybe you get more power output. But I left the university in 76 and somebody continued with 77, 70, I don't know.
Okay, thank you, Prof. Afifi. So any comment on that?
Just one question. What is the present experiments that the presenter put forward? What is the load for the turbine? Is it a generator or some other load?
Yes, it will be coupled to a generator.
What kind of speed targeting for the generator?
maybe you can repeat again, Dr. Wan?
Because the generators and the turbines sometimes are a mismatch. Most of the time, the generator requires high speed, but you are trying to get higher torque with a lower speed. So, can you highlight these things and what do you call your experience in this particular?
Okay, thank you. So
you understand?
it depends.
To share your experience.
One tak clear.
It's,
One your audio tak clear.
do you understand at all?
I can't hear you clearly.
I think a mismatch, Dr. Wan, in between the generator and the turbine. Maybe you can, Mr. Presenter, maybe you can comment a bit on the generator.
Okay, so for generator, if you want a better self-start ability at lower TSR, then you will choose higher number of blades. But if you want to operate at higher TSR, which is you have high structural performance, then you will choose for lower number of blades. So this is a trade-off between the features. So it really depends on the context.
Okay. Okay, so hopefully that answered the question, Dr. Wan. I mean, the signal, the reception of your internet not very good because we only listen a partial of the question. Okay, so thank you very much, Mr. Presenter. So that's from Nottingham University. So thank you very much for the participation, and we are very happy to have you in this conference. Thank you very much again.
Thank you.
Okay, so now we move to the next presentation. Okay, so maybe paper number 26. Okay, paper number 26. Maybe you can start share your slides while I'm announce your title and also the participants. Okay, paper 26 entitled Comparative Experimental Study on the Mixing Characteristic of Two Different Twin Jets. And the author of this study is A. Muturam and also S. Tanigayarasu. Okay, so this group from Prof. Taniga, okay, from Anna University. So we are very happy to have international paper. Okay, maybe you can start to share your presentation slide, Mr. Muturam. Did you hear my voice?
Good afternoon, sir. I can hear you.
Okay, good. You can start share your slide.
Just a second, sir.
Okay, try to change to presentation mode and you can immediately start the presentation after that.
Sir, is my screen visible, sir?
Yes, very good.
Yes. So good afternoon, one and all present over here. So my title is a comparative experimental study on mixing characteristics of two different twin jets. So I like to thank my supervisor, Dr. S. Tanigayarasu, Professor Head, Madras Institute of Technology. So here the contents are objective, literature survey, twin jet definition and applications, non-circular twin jet, necessity, advantages and disadvantages, experimental setup, radial Mach number decay profiles, shadow graph, conclusion. So here, this experimental study deals with the comparison of two twin jets, that is twin jets emanating from two different nozzle combinations, that is a circle and circle and circle hexagon configuration. here the nozzles used were convergent nozzles, and also the mass flow rate of outcoming of the outcoming jets from the exit of the nozzles are same, as the exit area of the nozzles are same, the mass flow rate are also same, and the nozzle spacing S by D is equal to 2, that is maintained same for both the cases, that is for circle and circle hexagon. And then the mixing characteristics were studied with the help of radial Mach number decay properties, and the radial the measurements were made at different axial locations in 11 different axial locations, such as 0, 2, 3, 4, 5, 6, 8, 10, 12, 16, and 20. So these are the axial locations. That is across the jet, I have taken the measurements radial across the jet. The flow visualization for NPRs 3 and 4 were also carried out by shadow graph technique. And I have done some literature survey. So first one, Sayali and Yasin, they have made an experimental study, that is initial interaction and region near the merging point of the unventilated two parallel plane jets. So they have used PAV, particle image velocimetry, and also proper orthogonal decomposition. And the aspect ratio taken for that two parallel rectangular nozzles, they have taken two parallel rectangular nozzles, aspect ratio 15.1. So they have found out that in the converging region, two jets resulted in large scale asymmetrical vertical structures between inner and outer mixing layers, as they have investigated for two parallel rectangular nozzles. They have asymmetric vertical structures between the inner and outer mixing layers. And the second one is this Syed Soban, that is they have also used PAV for investigating the near and intermediate field regions of jet issuing from 8 different nozzles, and they have found that the rectangular and elliptic jets has the highest mixing performance, and the least effective mixing is the star nozzle. And then Zaid Zhang, they have investigated both numerically and experimentally the characteristics of mixing regions. So the two jets deflect towards the inward facing region, and the deflection degree is determined by the jet spacing, pressure ratio, and turbulent intensity. And then the mean streamwise centerline velocity decay and entrainment in triangular and circular jets. And they have considered two isosceles triangular jets issuing from sharp edged orifice with apex angles 30 and 160 degree, and also a sharp edged orifice circular jet. And then ISEA BEF, he also investigated that effect of shape and Reynolds number. So to determine the mixing enhancement due to rectangular, squared, elliptical, and triangular nozzles. So here he found that all nozzles show similar behavior, especially in the jet far field, that is X by D greater than 10. So the far field, he found that all nozzles show similar behavior, especially in the jet far field. And then Ameya Dhruv, they have found numerical investigation of mixing in parallel jets. So a comparison between single jet, two jet, and three jet systems they have carried out. And then they found out that the weaker jet is attracted towards the stronger jets. So the three jet system compared to single and two jets, the three jet system, in the three jet system, mixing is more efficient than in the single and two jet system. And then Amitesh Kumar, he has made a study in a turbulent 2L jet consisting of wall jet and offset. And here he has identified that a recirculation zone, converging, merging, and combined regions by the numerical computation. And Karimpour, he has made a CFD study of merging turbulent planes. So here he has established the point at which the jets merge to form a single jet. So both measurements, that is between the numerical and experimental, so that showed that merging distance was independent of the nozzle width, provided that the centerline separation to nozzle width ratio was large. So this is a literature survey I have done, and this is the general flow field of a twin jet. here we can see the two nozzles represented as a U0. So from that, the jets were emanating from the two nozzles, and it actually merged at a point that is denoted by MP. So it is the merge point at which the flow becomes a stagnant. Actually, the inner shear layers of the two jets merge at that point, MP, where the velocity becomes stagnant. And inside that region, we have that recirculation zone where we have two contra-rotating vortices which occurs in that region. So that is a region of subatmospheric pressure. And after that merging point, we have a combined point. In that combined point, the velocity reaches the maximum. And the region between the merging point and the converge point, that is known as the merging region. And after that combined point, so at the CP, which is denoted by CP. So after that combined point, it actually, the twin jet actually behaves like a single jet, that is in the combined region. So we have three regions over here in the twin jet: converging region, merging region, and combined region. So from the literature survey, it is clear that most of the investigations has been carried out in identical and axisymmetric images. That is, they have taken both circle or rectangular or elliptic like that. So the uniqueness of this research is the combination of circular nozzle with a non-circular nozzle. Here I have considered circle and circle hexagon nozzle. So applications of twin jet. So interaction of two parallel jets from closely placed nozzles. So that is used to understand the fundamental physics of fluids in industrial problems such as gas turbine combustion chamber and air conditioner unit for automobile. As we have two jets coming from that air conditioner unit for the automobile, and then air curtain unit for refrigerating system. And in fighter jets and also in chemical industries, and a lot more applications of twin jets in space applications, and also in the fuel and air mixing inside the combustion chamber, etc. And then mixing of jets, what are the advantages? So it converts the heterogeneous physical system into homogeneous, and in many applications, enhanced mixing, that is nothing but the higher entrainment rate of ambient fluid with the core jet. So core jet is nothing but the jet that is within the boundary of the jet. So ambient is that the outermost layer of the jet. So there is a higher entrainment between the core and the ambient, and the large momentum transfer within the jet fluid. And this is the experimental setup. Gas compressor, moisture separator, storage tank, air filter, and then settling chamber, and pitot traverse mechanism, which includes. So this is the actual one. That is at Metro Institute of Technology, Chennai. And then considering about the circular nozzles. So in the beginning, at the starting of the research, in previous researches, that area of research was limited to circular jet because of its uniform flow pattern, ease of manufacturing that circular nozzles, and then ease of incorporation with gas turbines. And then actually we have two kinds of techniques, passive and active one. And passive mixing control strategies, that is based on geometric modifications, and other than that we can have that modifications like obstruction like body in the near field of the jet, and then introduction of tabs or notches at the nozzle, etc. So this comes under the passive mixing control techniques. So these alter the flow development downstream of the nozzle relative to the conventional circular nozzle. So it is also simpler and economical, and also from the literature survey, a high rate of decay and entrainment rate. So that is an indication of better mixing and asymmetry present in the non-circular jets, which causes increased overall entrainment rate and promotes mixing. So when the jets have a high rate of decay, when the decay is fast, and when the entrainment, that is between the core and ambient, so that also represents that indication of better mixing, and also that asymmetry in the non-circular jets. So that also increase the overall entrainment and promotes mixing. So and the need for non-circular nozzles. So for a better maneuverability and then feasibility and has potential to provide increased mixing rates, and jets from asymmetric nozzles spread and mix faster than asymmetric counterparts. And then it includes improved large and small scale mixing in low and high speed flows, and then it also enhances combustion efficiency, reducing combustion instabilities and undesired emissions. Additional applications, so that include noise reduction and heat transfer. And then advantages, the following advantages we have: deformation dynamics of asymmetric vortices, so that plays an important role in jet evolution. It was found out by Michael. And then increase the mixing with surrounding fluid, so that the core jet that can have a faster mixing with the ambient fluid, so increase the mixing with the surrounding fluid, and the efficient technique of passive flow control that allows significant improvement of performance in various practical systems at a relatively lower cost. Due to the presence of higher order instability modes, non-circular jets are more unstable. So that is the only one disadvantages for using the non-circular nozzles. So here I have considered the circular nozzle. Here that S is the spacing that from midpoint. So from midpoint to midpoint, and then diameter, that is the circle diameter, and here also in a circle hexagon we can see that nozzle spacing, that S, and D is the nozzle exit diameter. So S by D here I have maintained as 2 for both the circle and circle hexagon. And then result and discussion, I have considered that radial Mach number decay profiles. So here, as I already said, the radial profiles are taken for various X by D locations. That is this X 0, 2, 3, 4, 6, 8, 10, 12, 16, and 20. Here I have considered from 0 to 8. That is, as this is a near field, I have taken lot of readings in the near field. And then the radial profiles of circular twin jet and circular hexagon twin jet for Mach numbers 0.4 and 6.6. And here you can see the radial profile of the circle nozzle, twin jet from circle nozzle, and in the middle you can, that is considered as the center line. That is the midpoint between the two nozzles. So that is the center line. So actually, at the either side of the center line, you can see the profiles are similar, and it resembles the jet of a resembles like a single jet. And as I already told, that merge point is the point at which the velocity reaches the stagnation value. That is, the velocity is equal to 0. And here at the origin, we can see from this profile, that is between x by d is equal to 4 and x by d is equal to 5. So there lies the velocity which is 0, which becomes stagnant. And combined point, that is given by the maximum velocity, as we have seen in the general flow field of the wind jet. The maximum velocity is attained around x by d is equal to 16. That is at the far field. And regarding the Mach number 0.6 for circle nozzle, wind jet from circle nozzle, here we can see that merge point moves upstream. So as the Mach number increases, the merge point move upstream, and here the location, the merge point location lies between x by d is equal to 3 and x by d equal to 4, which can be clearly seen from the profile. So that at the center line, and also the combined point, and that also occurs here at x by d is equal to 12. Here also the profile is symmetrical about the center line, that on the either side of the center line, and also the spreading in both the radial profiles for Mach number 0.4 and Mach number 0.6. The spreading on either side is also same. And here we can see that a negative region in both the Mach number 0.4 and 0.6. So that negative region indicates the recirculation zone where that subatmospheric pressure exists. and also the contra-rotating vortices occurs. And next one is the twin jet from hexagon nozzle, that is for Mach number 0.4. Here we can see that unsymmetrical profile on the either side of the center line. So here that jet from the circular nozzle is attracted towards the jet from the hexagon nozzle, and the spreading is also different on the either side of the center line. And here the merge point, as we can see here, the merge point lies somewhat downstream as compared to m is equal to 0.4. That will be consolidated in the tableau column the next one. And then for Mach number 0.6 also, that profiles are symmetrical and the spreading is also different. And here we can have the consolidated radial, not axial, only radial profile for 0.4 and 0.6. So here that merge point 4 to 5 and for a circle, and then for combined point it is 16, and then merge point for circle is 3 to 4 and combined point is 12. And for hexagon, the merge point actually moves downstream, that is from 5 to 6, and for combined point it is 16. And for Mach number equal to 0.6, that is 4 to 5 and 12. So as we compare this circle and circle hexagon, the merge point moves downstream in case of circle hexagon, which shows that the mixing is delayed in case of twin jet from circle hexagon nozzle. And then that circle twin jet exhibits similar profile that I said. And then on the other side of the center line, as the velocity ratio is equal to 1, as the Mach number or velocity comes out from the nozzle exit of both the nozzles in that circle and circle hexagon are same, the velocity ratio is equal to 1. And the flow tends to resemble a single jet for downstream of the nozzle exit. So the distance from the nozzle to the point where the velocity profiles merge, that is where a single velocity peak. So that two jets that combine and finally forms a single peak which resembles the single jet. So that is a function of each jet's source conditions. As the Mach number increases here from 0.4 to 0.6, the location of merge point decreases. So it moves upstream towards the nozzle exit as we increase the Mach number. And then negative values, that shows the presence of recirculation region near the nozzle exit. The combination of circle and hexagon nozzle does not so much affect in mixing as in the case of twin jet from circle nozzle configuration. And the flow visualization was also visualized using shadow graph technique. And the nozzle pressure ratio has been taken for NPR 3 and 4 for circle and circle hexagon. And in circle for NPR 3 and NPR 4, we can see that both here that upper and bottom that resembles that same. So number of Mach discs and the number of shock cells, shock length. So both are similar in the circle nozzle for NPR 3 and NPR 4. So this shows that the momentum and the attraction and interaction created by both the jets are equal. And Mach discs are shown by the luminous part, bright bands in the shock, and we can see that the barrel-shaped shock. And when the jets come out of the nozzle exit, continuous compression and expansion waves occur, and there is a series of dark and light bands. So that bright band that indicates the Mach discs. And there is a normal shock in the center and the axis of the jet which is coming out of the nozzle exit. So that reduces the Mach number.
Mr. Muturam, please conclude your presentation.
Yes, sir. And also the for a circle hexagon. And here for NPR 3 also that nozzle, the top one is the circular one and bottom is the hexagon one. And here in NPR 4 we can see more number of Mach discs. And the circular jet there is a faster decay compared to hexagon which is at the bottom. So this shows that there is a mixing delay in the circle hexagon nozzle. And then also the number of shock shell length and then mag disc are also same in the circle injet. So these are the references I have made. So thank you all.
Okay, thank you very much, Mr. Muturam.
Yes.
Since we are run out of time, okay, I think for the audience that have a question, you can directly contact Mr. Muturam after this. Okay, so we move to the next presenter. Here we have paper number 28. Okay, so paper number 28. Please start share your slide. The title of the presentation is Numerical Analysis for Regression Rate Solid Fuel Doped with High Entropy Alloys in Hybrid Rocket Motor. So the contributor of this research or the author of this study is Siti Nur Faikah binti Asmuni, Izham Izzat Ismail, Muhammad Hanafi Azami, Nur Azam Abdullah, and Nur Huda Hidayah Nurdin. Okay, can start share your slide, please. So here we have our colleague from UIA, if I'm not mistaken, because I saw the name of Dr. Hanafi. So can you change to presentation mode, please?
So here you can see the slide.
Yes. How about the presentation mode?
Is it okay?
Yes, great. You can have a start now for 20 minutes.
Okay. Assalamualaikum warahmatullahi wabarakatuh and good afternoon for everyone. My name is Hamizam Ismail and I am under supervision of Dr. Hanafi bin Azami and we are from International Islamic University Malaysia, and inshallah today I'm going to present to you about the numerical analysis for regression rate solid fuel doped with the high entropy alloy in the hybrid rocket motor. Okay, this is my presentation outline where we have five important parts. For the first one, we have the brief introduction about the hybrid rocket motor and also the high entropy alloy. And then we have the problem statement, methodology, result and discussion. And also the last one is the conclusion. Okay, for introduction, we have here that the hybrid rocket motor is actually the combination of the solid fuel with a liquid or gas oxidizer as a propellant. And this hybrid rocket motor is actually bringing the advantages in terms of the safety, simplicity, throttling capability, fuel versatility, reliability, design flexibility, environmental friendliness, and also low cost. And this hybrid rocket motor is operated when the oxidizer is fed into the combustor. The fuel is then ignited and burned in the presence of the oxidizer. Okay, so that is the brief introduction about hybrid rocket motor. And we go to the high entropy alloy. This high entropy alloy is actually the combination of 4 or more metallic elements, and this combination will give the advantages in terms of the high hardness level, good wear resistant, and also resistant to corrosion and also the oxidation. Okay, the main problem has been faced by the hybrid rocket motor is actually it has a low regression rate, and this regression rate is dependent on the oxidizer mass flux, and therefore it will indicate that the rate at which the fuel burn is proportional to the amount of oxidizer flowing through the port, and this will governing to the hybrid rocket motor equation. And if you compare with the fuel regression rate of the hybrid rocket engine with the solid rocket engine, it is will be lower than the solid rocket engine. Therefore, in our research, we're going to have the energetic additive that will add to the fuel of the hybrid rocket motor, that it believed that it will increase the regression rate of the hybrid rocket motor. And our energetic additive is the cooperation with the material department, where we have the high entropy alloy as an additive. Okay, there is two types of the additive here, where you can see that the first one is the combination of the cobalt, chromium, iron, and also the nickel. And for the second one is with the presence of the aluminum. And this actually we will see how the effect of the aluminum inside of the additive here. And all of this additive will be added to the base fuel, which is paraffin. And also, if you see the research, paraffin itself is actually the evolution from the HTPB, because paraffin will give the better regression rate compared with the HTPB. And all of these properties will be input to the ANSYS software to have the simulation inside of the hybrid rocket motor. Okay, this is the solver algorithm where we have to define the suitable domain for the combustion model, and then we're going to define vaporizing surface as the wall boundary, and we will input the UDF user-defined function mass, energy, and also the momentum source at the boundary. We will solve some species and also the energy radiation, turbulence flow equation with the volumetric reaction, and then all of this data from the ANSYS software will be extracted as the temperature and also the regression rate, and then we can plot it inside of the Excel. And after that, we can tabulate the data and see the comparison of the result that we have. Okay, this is for the numerical model. We will have the SST-K omega model. This model is actually choose because of the better prediction inside of the flow separation, and also it will give you good behavior in the adverse pressure gradient. And also for the multi-phase, we have the explicit VOC with PLIC interface reconstruction. And this type of method has been successfully for the numerical simulation, and it is believed that it is going to give us the better, and also the result of the regression rate is same, like maybe not the same, but the result will be near to the experimental part. The next one is the combustion. We have the species equation with a laminar finite rate. Okay, this is for the computational domain where we have the meshing part for the ANSYS software that we need to put the inlet and also the outlet wall for the hybrid rocket motor, and then this is the vaporizing fuel surface, and this is source of the fuel that we also have assumed for the domain to carry out a steady state turbulence to reduce the computational effort. And there is no slip condition is imposed on the wall, and this meshing is sized to 0.002 to get more accurate solution. So this all of this part will be done inside of the meshing of the ANSYS software. Okay, for initialization and also choice of solver. Initialization we have made by referring to our model, our static firing model, but that one is still under process. But it is believed that the result might be the result will be compared with the experimental part, but all of this dimension will be follow of the dimension. And we have the oxidizer mass flux here, we have 8 and also the 14. This value will be get based on the literature. And next is choice of solver. The method that we are using is the simplex method, and we will use the Gauss cell center, and everything will be changed to second order. And also this type of method, it is in order to get the result based on the condition that we have. Okay, this is the result, and the analysis has been made for the paraffin. And as you can see here, for the mass flux at 8, you can see if you compare with the 14 mass flux, and then you can see that the combustion will be higher at the 14. And so from this graph, you can see very clearly how the regression rate inside of the hybrid rocket motor for the 8 and also the 14. So the increase in the regression rate along the streamline position, which is proceed by a slight decrease at a lower oxidizer influx, it will oppose to one of the higher value. And also the increase in the regression rate is due to the increase of mass flow rate along the stream. So this is and next is for the high entropy alloy, which represent of this kind of high entropy alloy. The result will be changed very much because of the higher for the 8 mass flux, the highest temperature will be provided at the below part here, and then for the 14 mass flux will be highest value is actually at the upper part edge here, and then from this result and also from this temperature we will see how the degradation rate inside of the hybrid rocket motor with the presence of the high entropy alloy. And from this graph you can see that this spike differ from the paraffin wax, by which we could see that the presence of the spike is most probably due to the energetic effect of the particle in the high entropy alloy. And also this energetic effect is due to reaction between the few particle mixed with oxidizer, and it will exciting it cause for rapid mass flow rate of the propellant. And you can see here that the difference between of the 8 and also the 14 here, the degradation rate is much higher compared to result before. Okay, for the next one is the with the presence of aluminum, and actually from this contour you can see that the change the presence of aluminum is actually change the behavior of the combustion inside of the hybrid rocket motor, but for egg for mass flow at 8 and also the 14, the difference is not much, but of course for the 14 the temperature will be higher compared with the egg mass flow. And the result here you can see that at the end of the position, the regression rate of the hybrid rocket motor nearly the same. Yeah, you can see that it is nearly the same, and the presence of aluminum is in this substance allow for the increment to occur, and this behavior is said to take place in the chemical substance due to the presence of an energetic particle. And the heat generated at the fuel surface excites the reaction between the high entropy alloy and also the oxygen. It is allowing a high degradation rate to take place. Okay, for the conclusion, you can see that based on the conclusion here, you can see that the implementation of the high entropy alloy for the egg mass flow, it is actually it will increase the regression rate about 84.6%, and also for the 14 mass flow it will increase about 74.5%, and this result is actually different, but it is the change is very small. So from here you can see that the regression rate will be higher for the without the aluminum inside of the high entropy alloy. So you can see that our finding is actually the implementation of the high entropy alloy inside of the hybrid rocket motor will increase the degradation rate, but it will depend on which element that we are using inside of the high entropy alloy. Okay, thank you.
Okay, thank you very much. Okay, so now I would like to open for question and answer. So we still have a few minutes left, so around 5 minutes for Q&A. So please raise up your question. Dr. Wan, maybe?
Okay, first question. Why do you need this metal in your fuel? So the first question. The second question, what are the effects? I mean, you are doing the digital calculations of the effects of the metal addition. Did you any result? Is there any result that you can compare your simulation with the experiments? Thank you.
Can you repeat for the first question, sir?
The first question: Why do you need the metals in the first place for your fuel?
Oh,
why do you have to add up all this metal to the fuel?
All of this metal is has been used to increase the degradation rate, because there is several method has been used to increase the degradation rate for the hybrid rocket motor, and energetic additive is one of the method has been used, but normally they are using, for example, they are only add of the aluminum, add of the boron, and for our research we have the addition of different kind of we just add four elements at the same time. So the addition is to increase the regression rate and the combustion efficiency inside of the hybrid rocket motor. And for the second question about the comparison with the result, the numerical result, right?
Yes.
For the comparison is actually
experiments, yeah.
the comparison is we can do the comparison, but the difference will be clear because of the dimension actually, because the dimension of hybrid rocket motor is different. And if I can show you the different, but if it is still below than 20 regression rate, it is still acceptable. That's it like that. It means the dimension and also the when we are using the software, then some of the assumption that has been made will affect the result for the regression rate.
Can I add up something, Prof. Wanzaidi? Actually, we dop metallic additive to increase the heat transfer to radiation. So that is the function for the metallic additive. So right now they are just putting one element, aluminium only, boron only, magnesium only. So why not we combine all this? Because we have patented one high entropy alloy, we call this HEA, and then try to do this, whether this will affect the regression rate or not, something like that, just to enhance the heat transfer through radiation.
Okay, because I am thinking on the other, from the other facet of the whole thing, thinking of the mass, what called the mass of the exhaust. Maybe the metal will increase the mass flow rate for the same volume. I'm thinking that way, rather than the heat transfer. Thank you very much.
Yeah, okay. Yelah, because when it evaporate, benda tu pun akan keluar sama, and then mass pun akan tingkat juga. Yes. That's
in that angle rather than the heat transfer angle.
Okay.
Okay. Thank you very much.
Thank you, Prof. Thank you, Prof.
All right.
Okay, thank you very much, Dr. Wanzaidi.
Thank you.
Any more questions from fellow audience? Please, we still have times for the question. Okay, in that case, thank you very much. Okay, thank you very much for the presentation from Mr. Izham Izzat and his supervisor, Dr. Muhammad Hanafi. Thank you very much. Here we have a good colleague from UIEM, University Islamic Malaysia, International Islamic University of Malaysia. So thank you very much for joining us. Okay, now we move to the next presentation. So here we have paper number 33. Okay, you can start sharing your slides. So the topics or the title of the presentation is Performance and Emission Analysis of Neem Oil Biodiesel with Pentanol Blend in Diesel Engine. Okay, so the contributor and the author of this research is Adamu Sulaiman, Omar Ali Umar, Muhammad Osman Kaisan, Ibrahim Umar Ibrahim, Shitu Abu Bakar, and Oyadiji Ayodiji Nathaniel. So please move to the presentation mode, Mr. Presenter, Mr. Shitu Abu Bakar. If possible, change to presentation mode. Is that possible?
Hello, can you hear me?
Yes, very good.
Okay.
Maybe a little bit louder will make it perfect.
Okay. Good morning, Mr. Chairman.
How about the presentation mode?
Oh, is it not on the presentation mode now?
A little bit to the right. Just now is okay. Change to the presentation mode. Just now is okay, is already shared, but
Okay.
you only have, or you just have to change to the presentation mode. Then it will be perfect.
Okay, I'm trying to set it on.
Okay, can you try it again?
Is it okay now?
Okay, but how about the presentation mode? Here at the lower part, and then at the lower part of the window. Okay, and then there will be a small icon below apply to all. Yeah, that one. Can you press that one?
Okay.
Ah, that's great.
there.
Okay, so now you can start and you have 20 minutes for the presentation together with Q&A. Please start now, Mr. Shitu Abu Bakar.
Okay, thank you for giving me the opportunity to make a presentation here. My name is Shitu Abubakar. I am presenting on behalf of Dr. Umar Ali, Dr. M.U. Kaisan, and the others. The title of my presentation is Performance and Emission Analysis of New Oil Biodiesel with Pentanol Blends in Diesel Engine. The presentation members have already mentioned the introductory parts. Despite the many significance in the use of diesel engines, emissions from these engines, such as carbon monoxide, unburned hydrocarbons, and particulate matter, have polluted the environment. Biodiesel is used in diesel blends in engines to reduce the emission of exhaust pollutants, except NOx. Biodiesel is the name given to a renewable diesel fuel that is produced from fats and oil. It consists of the simple alkyl esters of fatty acids, most typically the methyl esters. The resulting biodiesel usually has similar fuel properties as conventional petrodiesel. Early investigation of alcohols were mostly on lower alcohols, such as methanol, ethanol, but due to poor fuel properties of lower alcohols, for example, lower cetane numbers, lower heat of evaporation, researchers have recently focused on higher alcohols, such as propanol, which have higher carbon chains, cetane numbers, and heat of evaporation. The latent heat of evaporation, however, has a beneficial impact on combustion in terms of minimizing NOx. Statement of the problem. For humanity and its development, energy is one of the most important resources. Today, one of the global problems that plague us already is the energy crisis. The key sources of energy comes from fossil fuels, such as gasoline, coal, and natural gas. 80% of the world energy needs is contributed by fossil fuel. This leads to deep dependence on fossil fuels from everyday life. So, improving the quality of fuels has been a subject of research interest by scientists, especially in recent years, and finding an alternative to the fossil resources is also another area of interest to scientists and engineers. The related past work, Murad and Mahmoud investigated the influence of additions of alcohols, such as fuels additives, on engine performance and emission. Ethanol and butanol were blended with the gasoline. An experimental result showed that a significant reduction in the engine emission of carbon monoxide and hydrocarbons, a reduction of about 13.7% and 25.2% were recorded for CO2 and HC respectively. This shows that biofuels has the potential to reduce engine emissions. The work of Kaisan et al. 2020 found out that increasing the blending percentage of propanol reduces the emitted concentration of carbon monoxide, unbound hydrocarbon, and NOx. There is a research work by a researcher, Wang Wangtaku, 2016, who researched on addition of ethanol in a diesel fuel, and he established that the optimum appropriate amount of ethanol and gasoline blend was used, especially at low engine speed. And from his findings, he established that the addition of ethanol has potential in reducing the engine emissions. The work of Hussein and Ibrahim 2020 also shows that biodiesel as an alternative fuel to combustion ignition engine is a promising resources, and the findings shows that there was a reduction in the engine emissions with a slight increase in the brake specific fuel consumption. The work of Kumar and Churasha 2019 explained that the addition of ethanol reduces engine emissions of unbound hydrocarbon, particulate matter, NOx, and exhaust gas temperature. But it was also noted that it increases fuel consumption and also enhances engine brake thermal efficiency and brake torque. The major drawbacks of using bioresources, specifically biofuels, is the issue of high viscosity, high density, and the higher oxide of nitrogen. Because these fuels, they are oxygenates. They have excess amount of oxygen in them, and certainly when there is a combustion, during a combustion process, there will be a perfect combustion, and we may also have an excess oxygen after the combustion process. So NOx is usually provoked by high combustion temperature as well as the excess amount of oxygen. And these fuels also has lower calorific value. So now we want to see how we can reduce the viscosity of these biofuels and see how we can reduce the NOx emission, and something that we can do also to increase or to boost the lower calorific value. Based on this, we thought of introducing pentanol. Pentanol is a higher alcohol fuel. It has high latent heat of evaporation. And certainly when it has that high latent heat of evaporation, it will introduce cooling effect in the combustion chamber. By doing that, it will lessen the combustion temperature. And when the combustion temperature is lessened, certainly the nitrogen oxide emission will decrease. And it will also boost the miscibility of diesel and the biodiesel fuel. And due to the fact that this fuel also has a good calorific value, it will also boost the calorific value of the blend. So to minimize this drawback of the lead biodiesel, we introduce the pentanol as an additive to derive the advantages that this pentanol fuel has. The aim and objectives of this research. This is to investigate the performance and emission analysis of neem oil biodiesel with pentanol blends in a diesel engine. We followed the following specific objectives to realize this aim. First of all, we prepared the blends and determined their physicochemical properties. The essence of determining the physicochemical properties is to make comparison with the conventional, that's the baseline fuel, which is the diesel fuel. So if our blend has properties similar to diesel and is aligned with the ASTM standard, then we can say that our blend is promising and can be used in an internal combustion engine. That was why we characterize it. We checked the physicochemical properties of the fuel to ascertain its suitability and to compare it with the baseline fuel, which is diesel fuel. We also did an investigation. We also investigated the performance of the blends in the stationary combustion ignition engine. Basically, we were able to calculate the brake thermal efficiency of the fuel, and also realize the brake specific fuel consumption using these blends. And we've also assessed the emissions level of the blends. We finally concluded about the blends that we prepared. The methods, materials and methods, we used a 4-stroke air-cooled horizontal single cylinder diesel engine. The specifications are given on table 1. And we've also used a gas analyzer manufactured by Nanhua, Guangdong, China, to measure the exhaust emissions. This is the specification of the engine. It has a rated power of about 2,600. They are cooled the rated speed of 2,600, rated power of 2.43 kilowatts. And the make is Super 165F. This also the specification of the gas analyzer, Nanhua, and what can be obtained from this gas analyzer and one can So here is a table showing the samples that we prepared. You can see that number 1 is D100. D100 means the pure diesel, which is the baseline. So all comparisons are based on the baseline. Second is 70% of diesel, then 7% of the biodiesel, and 3% of pentanol. Likewise, the number 3, 70% of the diesel, 24% of the biodiesel, 6% of the pentanol. So we prepared 5 samples, and the experiments were carried out as stated earlier using the compression ignition engine at 6 Nm torque, and it was based on the ambient condition of our location, which is the 1 bar and 35 degrees Celsius. So this shows the pictorial view of the constant compression of the compression ignition engine. And this is the engine instrumentation where we set the torque, we measure the fuel consumption, and other parameters. The emission gas analyzer, this depicts the picture, shows the screen view where we can measure the burnt hydrocarbon, the CO emission, and the rest. The results of our physicochemical properties of the biodiesel is given here. We've shown the calorific value to be 34.42, the density, the viscosity, the 4 points, the flash point, and the acidic value. So this is for the biodiesel. And we made comparison with the standard, that is the ASTM standard. This calorific value of diesel is usually 42.49 from literature, 4.67 from literature for pentanol, and 4.42 for biodiesel, which is one we realized. And this is the ASTM standard. The ASTM standard said the calorific value should be in the range of 33 to 45. It's within that range, and the pentanol is also within that range. So the calorific values of diesel is by far higher than that of the pentanol and the biodiesel. So we can infer from here that if we are using biodiesel and pentanol, then certainly we are decreasing the calorific value of the blends. Because if we combine these three very values, certainly, and these 5 points shows the inevitability of the fuel, how fast the fuel catches fire. The ASTM standard said it must be less than or equal to 100, and our value for biodiesel is also a bit higher, but this could be due to some errors. But that of the pentanol is also in line with the ASTM standard, and the densities, we can see that the density is within the range. The kinematic viscosity is also within the range. The molecular weight not able to determine for the biodiesel, not also given as the ASTM standard. So figure 4 shows the density of biodiesel pentanol biodiesel blend compared with the ASTM standard. This is the maximum ASTM standard and this is the minimum. So the pure biodiesel is still within the range, is still within the maximum and the minimum. We can see that all the blends satisfy the ASTM standards. The reduction of density from B100 to B1812 was as a result of increase in the pentanol percentage, a respective decrease in neem oil volume percentage with the constant volume of diesel, which reduces the viscosity of the fuel mixture and the mixture rate. Also shown the brake power. You can see that blend B21P9 has the highest brake power, and we can say that the biodiesel blends and the pentanol blend shows higher brake power compared to the baseline fuel, which is the diesel fuel. The engine brake power produced by the blended samples was higher than that of pure diesel. This shows that fuel quality in terms of engine brake power has improved with the introduction of pentanol and biodiesel. Increased from B27P3 to B24P9 is as a result of respective blends having less viscosity and density. Because as we are introducing the pentanol, we are decreasing the viscosity of the diesel biodiesel. This will increase the pressures. Why increase the B12 sample can be attributed to having a lower heating value as a result of higher pentanol percentages. Sample B21P9 has the highest brake power among all the samples tested. And this shows the exhaust temperature. Hello?
Please speak louder.
Okay, this shows, figure 6 shows the exhaust gas temperature. You can see that the diesel, the B27P3 has the highest exhaust gas temperature, but B21P9 has the lowest exhaust gas temperature. The result shows that exhaust gas temperature was also affected by the changes in the percentage of neem oil and pentanol in fuel blends. But B27P3 exhaust gases temperature increased as compared with the pure diesel, but with pentanol percentage by volume of 9%, it falls below that of the pure diesel. Brake specific fuel consumption. The result shows that pure diesel has the lowest brake specific fuel consumption value under the same conditions as compared with all other blends fuel samples, while B21P9 had the highest BSFC compared to the blends. In the case of fuel blends containing a small amount of pentanol, an increase in the BSFC combustion process can be due to the improvement in the combustion process, which causes by the inclusion of the extra molecule of the oxygen in pentanol. But in my previous slides, I've shown that the biodiesel and the pentanol has lower calorific value compared to the baseline diesel. So since the biodiesel and the pentanol fuels has lower calorific value, certainly it will translate to higher brake specific oil consumption because the engine will take more to burn and produce power because the biodiesel and the pentanol has lower calorific value.
Please conclude your presentation, Mr. Shitu. It's about the time now.
Okay. So we can see that the emissions were reduced also by 3.3%. Certainly, in general, the emissions were reduced, including the NOx emission. And we were able to realize that because of the introduction of the pentanol, ideally burning the biodiesel and the diesel will increase the NOx emission. But introducing the pentanol has decreased the combustion temperature. And in this way, we're getting lesser NOx emission. In conclusion, it was noted that fuel blend with high pentanol percentage of about 2% by volume have the best engine emission properties as compared to the rest of the blend and the pure diesel fuel, with about 47% reduction in the hydrocarbon emission when compared with petrol diesel, and also with the lowest NOx emission among the blended samples. While B27P3 was the sample with the lowest carbon monoxide emission, which recorded a decrease of about 3% compared to petrol diesel. B27P3 was the sample with the lowest carbon monoxide emission, which recorded a decrease of about 3% compared to petrol diesel. Considering the experimental analysis, that follows, that we can make conclusion that addition of pentanol to the diesel mean biodiesel have significantly improved most of the engine performance and the emission parameters. It was finally concluded that the addition of alcohol like pentanol to the blends of biodiesel improved the fuel quality and engine performance and the emission. These are some of the references we've consulted. That is the end of the presentation, and thank you for the audience.
Okay, thank you very much, Mr. Shitu Abu Bakar. So it's a great presentation. Okay, but unfortunately, we don't have time for Q&A. So maybe for the fellow audience who has a question that you want to ask something to Mr. Abu Bakar, you can message him personally after the conference. Okay, so without any further ado, let's move to the next presentation. So here we have paper number 38. Okay, so paper number 28, you can start share your slides. Okay, so while I'm reading the title of the project, here we have the thermodynamic analysis on a new revised OTEC cycle using ammonia. So here we have Mr. Muhammad Aiman Wafi Suruji, me as the co-contributor, Nazri Nasir, and then we have Norazila Osman. Then we have Dr. Wan Zaidi Wan Omar, and the last one we have Dr. Shabuddin Mat. Okay, so now I leave the floor to Mr. Aiman to continue the presentation. You have 20 minutes from now, and you can start your presentation.
Okay. Wait. Okay. Assalamualaikum warahmatullahi wabarakatuh, and very good day to the chair, Dr. Nazri, Professor, Dr. Lecturer, and all the participants. My name is Muhammad Aiman Wafi bin Suruji, and today I'm going to present thermodynamic analysis of new revised OTEC cycle using ammonia refrigerant. And the author of this paper is me myself. I am Dr. Muhammad Nazri bin Muhammad Nasir, Dr. Norazila binti Osman, Dr. Wan Zaidi Wan Omar, I am Dr. Shabuddin bin Mat. So without further ado, let's start with the introduction. So as we know, natural gas and coal are the main source for the power generation in Malaysia, and both source has carbon dioxide as a byproduct, which affect the environment such as global warming. So alternative sources are required in order to reduce the environmental effect. So and OTEC is one of the solution. So what's OTEC? OTEC is a Rankine cycle that used to generate electricity by utilizing the temperature difference between ocean surface water and ocean deep sea water. And for the basic OTEC cycle, it consists of 4 main components, which is pump, evaporator, condenser, and turbine. And the working principle is the refrigerant will be pumped into the evaporator, and the refrigerant will be heat up by using the warm surface seawater, and the heated refrigerant will be fed into the turbine to rotate the turbine and at the same time generate electricity. And the refrigerant that come out from the turbine will be fed into the condenser to be condensed back into a liquid state, and the condensed refrigerant will be fed into the pump bag to complete the cycle. And this is the issue of the OTEC cycle, where the basic OTEC cycle efficiency is actually at low thermal efficiency level, which is only up to 3.1%. And many revised OTEC cycle improve the thermal efficiency, but at the same time, the cycle become more complex, which cause the significant increase of the capital cost. So the approach used in this research is to design new revised OTEC cycle, where we revise the OTEC cycle to gain significant thermal efficiency improvement, at the same time minimize the modification to avoid significant increase in the capital cost. And on the other hand, we do the thermal efficiency quantification to study on how the mass fraction of motif pressure ratio and the surface seawater temperature affect the thermal efficiency of the new reverse OTEC cycle. And the objective of this paper is to develop an algorithm for the thermodynamic analysis on the MATLAB using a coprop library as a thermodynamic property solver. On the other side, we quantify the thermal efficiency by varying the surface seawater temperature, mass fraction of motif, and the motif pressure ratio. And moving on to the methodology, where this is the proposed model for the new revised OTEC Rankine cycle, where we call it SEP OTEC. It is actually extension from the SOTEC and EP OTEC cycle, where we take out the solar collector part from the SOTEC and put in between turbine and the evaporator. And while the liquid vapor ejector, motif pump, and distributor, we take out from the EP OTEC and place in between the turbine and the condenser. So the working principle of this proposed model is the refrigerant will be pumped into the evaporator, and the refrigerant will be heat up until using the surface seawater until it reach saturated vapor, and the saturated vapor will be fed into the solar collector array, and the solar collector will further heat up the refrigerant until it reach superheated vapor, and the superheated vapor will be fed into the turbine, where it will rotate the turbine and at the same time generate electricity. The refrigerant come out from the turbine will be fed into the secondary nozzle of the ejector. On the other hand, another stream from number 8 come out from the distributor will be pumped into the primary nozzle to drive the liquid vapor ejector, and then the primary nozzle and the secondary nozzle fluid will be mixed into the mixer area in the liquid vapor ejector and diffuse out through the diffuser of the ejector, and the refrigerant will be fed into the condenser to be condensed using deep sea water, and the refrigerant will be fed back into the distributor and to the main pump and the motif pump to complete the cycle. And this is the input parameter that we consider during the analysis. And this is the analysis assumption and condition that we use in order to allow us to do the calculation of the model, and at the same time simplify the analysis of the SCPOTech cycle. And this is the analysis flowchart of the of the new revised Renka cycle SCPOTech, where as we can see, the calculation is start at the evaporator and solar collector array. This is because we already have all the information before we start the calculation, and after that we start to assume the T1, which T1 value, which is the evaporator temperature inlet, and by assuming that, we can proceed the calculation by calculate the evaporator inlet and Motif pump outlet. And after that, we proceed with the ejector calculation, where we can see that it involves a lot of iteration in order to make sure that our assumption value are correct and suitable for the cycle. And then after the ejector calculation, we proceed with the condenser outlet calculation. And for the first time, we will recalculate the main pump power and the Motif pump power to include the isotropic efficiency consideration. And then after that, the value will be fed back into the evaporator inlet calculation and until condenser outlet calculation. And before we end the analysis, we check the entropy value of the condenser outlet and the pump main pump or Motif pump entropy. And this condition is important because in our condition we set that the pump considered isentropic, so the entropy value for pump and the condenser outlet should be same. And then after we obtain to achieve that, we will adjust the T1 value until we get an equal entropy value. And then after that, we can proceed to the thermal efficiency and pressure drop ratio calculation. And the output of the analysis is the power of the turbine, main pump power, Motif pump power, heat load of the evaporator and condenser, pressure drop ratio, thermal efficiency, suction pressure, mass flow rate of the Motif and the evaporator. And so this is the result of the analysis, where where we can see that when we vary the surface seawater temperature, the thermal efficiency have a linear relation to the surface seawater temperature with a positive gradient. And this is when we varies the mass fraction of Motif, where we can see that the suction pressure decrease when as the mass fraction of the Motif increase until it reach the minimum point, and then it start to recover again due to the significantly increase of the density at the secondary nozzle outlet of the ejector. And this is where we can see that the maximum sorry, I got a problem with my slide. Wait. Okay, this one. This is we can see that the maximum point of the efficiency, where the cycle able to achieve 6.83% efficiency at the mass fraction of Motif 0.1536. But we noticed that the maximum efficiency are not aligned with the maximum turbine power. This is due to the increase of the turbine power and the increase of the total pump power are not equivalent. And moving on, this is the Motif pressure ratio varies from 0.53 to 1.70, where we notice that the efficiency significantly increase as the Motif pressure drop motif pressure ratio increase, and this is due to the turbine the significant decrease of the total pump power, and we can see that after it reached the maximum point, the efficiency start to decrease gradually. This is due to the turbine power itself that drop a lot, but the total pump power not drop as much as the turbine power. And the final finding of this research, we can say that we are able to achieve 120% improvement compared to the basic OTEC cycle, 106% improvement compared to the SOTEC cycle, 70% improvement compared to the EP OTEC cycle. And as a conclusion, the improvement obtained where we can say that we are able to have a maximum thermal efficiency of 6.83% efficiency. It is 120% improvement compared to the basic OTEC cycle, and we obtain significant improvement with minimum modification. And this is important because the improved thermal efficiency will reduce the component size and the reduced capital cost to build a power plant that to generate the same amount of power. At this moment, the diameter of the nozzle of the ejector is only assumption, but we noticed that the diameter of the nozzle of the ejector have a significant effect on the system, where it can affect the optimum value of the other parameter. And for the future work, we suggest to include optimum geometry of the ejector and to consider the solar radiation as a manipulated variable. And last but not least, thank you to UTM, UTM OTEC and SATRAP program for the under Ocean Thermal Energy Conversion project for the funding and the big cooperation. And I think that's all for me. Thank you.
Alhamdulillah, thank you very much, Mr. Muhammad Aiman Wafi. So now I open for a question from a fellow audience. So please ask a question to Mr. Aiman because we still have around 5 minutes for Q&A. So anything that you want to ask? Don't worry, you don't have to be very technical. You can also ask a general question. Okay, if not, then maybe I'm the one that will ask question. Okay, so maybe Aiman, you can explain about your finding. Okay, so you have this 120% of improvement. Okay, so that should be 20% more than the previous one. Okay, 1 and 20% more than the previous one. So how this consistent with the previous finding? Okay, because we know that everything that we got at the end of the day, at the end of the analysis, before we present to the people, we want to attract their confidence. Okay, so we want to make sure that they're confident. So the way that we can ensure that their confidence is by correlates our finding with other previous results. So maybe you can explain a little bit on this.
Can you simplify your question?
Okay, can you relate your findings so about the thermal efficiency improvement, okay, with the previous study? Okay, so how this 1,120, okay, consistent with the previous research? Are they got the same thing or they are got totally different than what you have here?
Actually, for the previous research, they don't have this kind of cycle, so I cannot compare yet. But for the SOTEC, like they have 3.3%, and they claim they will have at least 2 times improvement, where 3 how you say that? Not, I'm not sure how to answer the question, but I think not much I can say about this your question.
Okay. Because everybody interested, everyone who work in this cycle, in this thermodynamic cycle, they definitely want to know the efficiency. Okay, so this a very big issue, something important. Okay, but because your work is more on the computational work, and then supposed to be that you have to relate with experimental works, but the problem now you don't have the experimental setup. And the alternative, you have to compare with the previous study. But the problem is there's no study that exactly the same as what you have at the moment. Okay, that's also the another problem. Okay, so I think it's a good thing in future that you can figure out the method to validate your findings so that you can gain confidence for you yourself and also for the audience or readers that jump into your study. Okay. Okay. So thank you very much, Mr. Muhammad Aiman Wafi. Okay, so last but not least, we move to our last presentation. Okay, you can start sharing your slide. So here we have paper number 39. Okay, paper number 39. Here we had the title of the presentation is the effect of flow coefficient and rotor radius ratio. Okay, rotor radius ratio on radial turbine analysis. So here we have Mr. A.R. Jasni, Mr. S. Manso, N. Osman, M. A.B. Wahid, N.A.R. Nick Muhammad, and then me, N. Nasir, and also the last one, M.N. Dahlan. So now, please change to the presentation mode, Mr. Ahmad Razin. And you can start your presentation 20 minutes from now.
Yeah, Assalamualaikum warahmatullahi wabarakatuh, and good evening to everyone. So thank you to Dr. Nazri and ISEA for this opportunity. So today I would like to present about the effect of flow coefficient and rotor radius ratio on a radial inflow turbine analysis. So basically, the design of this radial inflow turbine is based on OTEC system, 3 kilowatt OTEC system. So which we will study the effect of flow coefficient and the geometry radius ratio. Okay, as we know earlier, the ocean thermal energy conversion or OTEC is where we generate electricity by utilize the temperature, seawater temperature, and depth sea surface water temperature and depth sea water temperature. So it has a low temperature gradient between the surface temperature and the depth sea water. It's about 11 degrees Celsius for working fluid to work on the turbine. So OTEC basically use organic Rankine cycle as the thermodynamic cycle. So the general refrigerant used is ammonia R134A and R22, the freon. Okay, because of the low temperature gradient, the design of the turbine have to be give more efficiency to generate electricity. So in order to improve the whole OTEC cycle system. So in turbine design, most of the previous researcher use non-dimensional parameter to design turbine characteristic. So in this research, I will focus on flow coefficients and rotor radius ratio. So flow coefficient is flow coefficient is the characteristic of the mass flow behavior, which is defined as a ratio of the exit meridional velocity, which is flow velocity at the outlet. Okay, here is the turbine configuration for rotor and the velocity triangle. Okay, so the exit meridional velocity is here, and the rotor inlet blade rotational speed, which is the blade speed in RPM. So in this case, I use 50,000 RPM as a design speed for rotational speed. Okay, so meanwhile the rotor radius ratio is I use 2 radius ratio, which is the exit shroud to rotor inlet radius ratio, which is the ratio between the outlet shroud, the tip radius from the center of the rotor, and the inlet radius of the rotor from the center. So the exit shroud to rotor radial inlet is a ratio between this radius and inlet radius. And the second one is hub to shroud radius ratio is ratio between the radius on the hub or the shaft of the rotor and the tip radius of the rotor. Okay, so the methodology I adopted is I use thermodynamic input to design to give assumption towards the non-dimensional parameter of the, to design the turbine. Okay, so the thermodynamic input is based on 3 kilowatt OTEC cycle system, which is the inlet temperature and the outlet temperature is 24 and 13 degrees Celsius. Okay, and I use ammonia as a working fluid, and the mass flow rate is about 0.12 kilogram per second. So the in one-dimensional inline design, so common radial turbine have 4 basic components. So in this case, I will not include stator because to avoid any manufacturing incapability, because the size of the turbine will be small, will be very small. In fact, it cannot be manufactured. So and this research paper will focus on vendors radial turbine, which include the volutes design and the rotor design. But in this presentation, I will focus on the rotor design itself. Okay, so the rotor design, the non-dimensional parameter I use is velocity ratio, flow coefficient, and rotor radius ratio. So the velocity ratio is ratio between inlet rotational speed with the inlet radius. So this ratio, velocity ratio, I use to estimate the value for inlet radius of the rotor of the turbine. Okay, so from the non-dimensional parameter, all this geometry is defined based on that parameter. So next, I will use I will go to mesh generation after the design is finalized. Go to mesh generation for mesh independent study and simulation by solver for, and I use previous researcher which designed 2 kilowatt OTEC turbine for validation of my simulation approach. Okay, this is OTEC system schematic diagram. So this is the input and output condition for turbine. So I will focus on condition at 3 and 4. Okay, so the inlet temperature is 24 degrees Celsius and outlet temperature is 13 degrees Celsius. The pressure is about 948 kilopascal, and the pressure at outlet is about 682 kilopascal. So the turbine will be fixed in 15,000 RPM, which is the design condition for the turbine. Okay, Okay, so this is the base design. So the base design, I will set up the base design and compare with other design with this design that I put the variation of flow coefficient. So the basic design is the first ratio, which is the ratio between the shroud outlet and the radius inlet is 0.7 maximum, because more than that we will face the difficulty in manufacturing. So the second parameter is radius between hub and the shroud is about 0.4. So the inlet radius will fix at 30 millimeter for the whole design, and the blade height is also fixed at 7 millimeter. So turbine rotation speed is 50,000 rpm. Blade angle is fixed at 90 degree. Flow angle is fixed at 5 degree from the tangential direction. Okay, this is my meshing for mesh independent study. So I use tetrahedral element with about 3.2 million number of nodes, which is the fine meshing at the near the turbine blades, which is about 0.01 millimeter. Okay, so the Cfd approach that I use software ANSYS Fluent. So I use simulation of three-dimensional steady-state compressible flow, which K omega SST as the turbulent models. Okay, so I divide into two domain, which is the stationary domain and the rotating domain. So the volute casing and the outlet pipe is remain as a stationary domain, while the rotor is made as the rotating domain. So this part is connect in the domain interface model. So I use the plane-to-plane movement. So the working fluid I use is the model by West-Redlich form, which is ammonia model. Okay, all the wall is considered to be no slip condition and in adiabatic condition. Convergent criteria is up to 10 to the power of -4 for root mean square criteria. So this is the mesh independent study, and also the validation of the turbine model, which I compare my simulation approach with 2 kilowatt turbine model from Nintesh. Okay, so the simulation agrees reasonably, and similar approach is used for the simulation design along this research. Okay, so the result and discussion. So this is all the turbine geometry parametric. So all the shaft radius and blade outlet height is varied based on variation of loading coefficient, which is from 0.12 to 0.30. So as the loading coefficient increase, the shaft radius will be decreased. So which is the base design is 21 millimeter. So the last design is 15 millimeter. So the after 0.3 loading coefficient, there's no necessity to continue to 0.35 because the blade height is getting smaller, so it will cause difficulty in manufacturing. So the study is limited into 0.3 loading coefficient. So the ratio of shroud exit shroud radius and the inlet radius is decreasing along the way with loading coefficient increasing. So the ratio between hub and shroud is increasing. Blade outlet height is also decreasing. They depend on the shroud radius because the hub radius is constant. So the blade is is getting smaller and smaller. The meridional speed, which is the meridional speed at the outlet, increase along as loading coefficient increase. So the torque and power also increase. So this cause the maximum power at 0.3 loading of loading coefficient, which is the torque is about 0.6181 Newton meter. Here, this is the turbine efficiency with respect to the variation of flow coefficient. Here, the first graph show the turbine efficiency based on flow coefficient variation, which is the best efficiency is about at 0.3 flow coefficient, which is about 85%. Meanwhile, the radius ratio, both radius ratio is about 0.5 to 0.53. So it's about a similar value. Yeah, this is the flow analysis from the model 5, which is at the flow coefficient of 0.3. So the first figure show the velocity vector of turbine design. Here we show the inlet velocity is at height of 190 meter per second, okay, and decreasing towards the outlet of the turbine. Here the second figure is about turbine pressure contour at 50,000 RPM. So the model is model 5, which is at 0.3 flow coefficient. So as we can see, the pressure is decreasing. The pressure distribution is decreasing towards the outlet, which is high at the inlet of the turbine blade. Yeah, this is the rotor produced torque with respect to meridional velocity at outlets. So as we can see, the flow is the torque is increasing toward the flow coefficient 0.3. So the velocity is increasing about towards the variation of flow coefficient. But however, we as we can see towards 40 and 45 meter per second, the torque is about to constant. So there's no necessity for me to increase more of velocity, which cause the outlet of turbine would be smaller from the inlet of the turbine and the turbine blade to avoid from manufacturing difficulties. Okay, the second figure show the velocity vector for turbine in a meridional view. So as we can see, the flow of the ammonia is high at the inlet and toward the outlet is decreasing. So the ratio between the velocity at inlet and outlet is about 0.25, which is at inlet is about 190 meter per second and the outlet is about 42 meter per second. Okay, as a conclusion, so this study highlight the preliminary analysis on turbine rotor geometry, where the exit shroud to rotor inlet radius and a hub to shroud radius, which is rotor radius ratio, is considered as a main parameter in 3 kilowatt per tank system. So both rotor radius ratio is defined based on the flow coefficient, which is from 0.12 to 0.13. So from the Cfd analysis, the high efficiency occurs at flow coefficient of 0.3, which is about 84.3%. So this value is increasing about 13.9% from the base model, which is flow coefficient of 0.12. Okay, so the 0.3, the model 5 is the shroud radius is about 15 millimeter, and the blade height is about 7 millimeter, which is similar to the inlet blade height, or also 7 millimeter. So the exit shroud rotor radius and up to shroud radius is about 0.5 and 0.53. So the power output for the model 5 is 3.239 kilowatt with a torque about 0.6 Newton meter. Yeah, that's all for me. So I would like to thank the MOE and JICA for sponsoring this project under SATRACS. Okay, that's all. Thank you.
Okay, thank you very much, Mr. Razin. Okay,
Yes.
so Mr. Amar Razin. Okay, so now I open for question from a fellow audience. Please ask question. So any question? Okay, so if not, then let's allow me to conclude our session.
Okay, thank you.
So if possible, please open your webcam so that I can take a snapshot of this session number 4. Okay, so another things, while waiting for others, okay, so while waiting for others, please make a vote for the best presentation, okay, before you leave. Maybe you can state the name, or maybe if you forget the name, so let's allow me to share the presentation again. Okay, so here you go. I think you get it. Okay, so if I recap again, so we have paper number 12, okay, from Mr. Muhammad Ajwad, and then we have paper number 14 from Mr. Iskandar Zulkarnain, okay, and then we have number 20 from Mr. Koh Ho Wong, and then 26, Mr. A. Muturam, and then 28, Mr. Izham Izzat Ismail, and then for paper number 33 from Shitu Abu Bakar, and then 38 we have Muhammad Aiman Wafi, and the last one, paper 39, you have Mr. A.R. Jasmi. Okay, you can put the vote in the snapshot, in the chat box. Sorry. Okay, so with that, I wish you all the best for your presentation. Okay, let me take the snapshot first before I forget. Okay, so I will take the snapshot. Okay, so I got where's the alarm? Sorry. Okay, so with that, I wish you all the best with your future research and development, and also your study. So if possible, okay, I really advise you to take this platform, okay, so these seminars or this conference as a platform for you to build up the relationship with other researchers. Take this opportunity to understand not only about your research, but also research from other people, other researchers from other universities, local and international. So is a good platform, especially for a few of student here, okay, especially my student. This will be the first experience for you to get involved in a conference like this. Okay, hopefully that you can gain some experience. Okay, other than that, please fill in the online attendance form. So all those included in the chat box. Okay, I give you the link. Okay, So other than that, at the end of, I just want to say thank you very much. Have a nice weekend. Assalamualaikum. And please don't forget to put your vote for the best presentation, but you have to exclude yourself, okay? So I mean you have to vote for other people. Don't put your name, you vote yourself, okay? So please vote other people, okay? So that it might be helpful for the organizer to choose the best presentation of session number 4. Okay, I will stay in this Webex account so that you have more time, okay, for you to choose the best presentation before you leave. Okay, that's all. Thank you very much. Assalamualaikum and have a nice weekend.